All right. Let's make the conclusion having connecting back to simple statistical approach to the complex machine learning approach. You can, in this morning we have done also simple logistic regression connecting to the high dimensional discriminant analysis, etc. Now, as I said, that many of the nonlinear model we can actually look at as a general linear model, and that's the way you will see. And that will give me the connection that neural network is nothing but a set of nonlinear regressions. And since nonlinear regression is connecting to the general linear model, I'll connect back to the general linear model. And what would happen? Essentially, when you are here, you have over-parameterized machine takes lots more parameter, so there will be penalized estimation. Then we'll connect back to whatever we learn this penalized estimation. So hopefully that would be right. But I won't spend too much time on these things, but still you should get some idea why the nonlinear models even developed. But in terms of system development, it has number of advantage or some kind of similarities with whatever we have been doing. So let's just as usual, I'll start with one of these typical data. It is small data set, you can see. Some of you know what is called Pharmaco Kinetics. Again, it is related to drug development. So when you take a dose, so basically apply a dose to a subject and blood sample taken over a number of time, and then you like to see what's the effect of this drug in your different blood cells. And your body is kind of compartment numbers, or when the blood passes through your body, it goes compartment by compartment. So something in engineering, biomedical engineering, is called the compartment model. So what is compartment model is nothing but a bunch of differential equation. I'll show you some simplistic one, because already I told you that nowadays what we have been working thousands of differential equation which can model your heart, but the concept was there even 1980s or so. So typically the observations is in a statistical context, the observations what you get eventually the concentration of drug in blood or plasma, that's the way the concentration is. And typical after extracting everything, a data may look like, suppose there are 6 patients, and over the time at the final compartment what the measurement which is concentration is the given here. Okay, so it's kind of a discrete time point. And this data was collected those days when we didn't start talking about the functional data. What you have heard us and Professor Dhar was giving you these things. Typically this data also you can look at as a functional data, because blood is also passing through your body continuously and you can actually capture through the image in general way. So these are your the drug concentration in your blood. So once you put that drug, then what is the concentration in your blood? That's a continuous phenomena. But 1, 2, 3, 4, 5, 6. These are kind of 6 individual patients. You are using the same drug. It's kind of a replications gives you how it's propagate in your body, and then in your body you are taking the observations at different time points, because you cannot observe throughout this whole time period. So one way you can think about this is a simple time series type of data, so many time points, and these are the replications. So it's essentially we call it a longitudinal study, but it is nothing but multiple short time series. Okay, so since the technology was not there, everything 1980s, this was the way you collect the data. Nowadays possibly you will have lot more data. So here is I'm plotting one of the for one individual, how the blood concentration dynamics, that means over the time how it goes. And what is the idea? You have to basically estimate the blood concentration dynamics so that they would know. So in many ways, one simple example, if I know that when the concentration goes almost 0, that's why doctors oftentimes prescribe, I cannot give you this medicine before 6 hours, before 10 hours, because they have to know the dying period and how it goes. Okay, so it has big implication than the short story. But then the idea is how to estimate the curve. And if you can estimate the curve, then any given time point, the doctors might have idea what's the level of concentration is there, right? If I can draw a smooth curve, then for any given time point, I would know. So basically, suppose you give one drug, then probably as the way you are expecting, the patient did not respond accordingly. You are thinking about a next drug, but before that you have to understand what's the level of that drug in your blood already. Otherwise, it might contaminate it. So that's why it is very, very important to understand from the doctor's perspective what's the blood level, the concentration level inside the body. Okay. So then tell me what kind of model you can fit. Certainly, as the way we have learned, simple linear model does not work, right? You can think about some nonlinear model, etc., but it's not so easy to do. So definitely statisticians didn't have much at the beginning. As I said, that it was coming from the biomedical engineering background. So we are the statisticians, always will attempt to, okay, we can make it some nonlinear, non-parametric model, etc. But note that we can actually have the observations only few time points and then only few of the replications. So fitting a non-parametric model may not be making any sense here. So you have to think about a model which can be only few parameters because you have only few data sets. Although ideally you could have observed many more data sets, but they don't. So in experiment. So here's typical picture how the way blood concentration change. So here is the dose. When you give it to here at the time point t, or you can think about this compartment in your upper body compartment or upper shell compartment. Then from this compartment at the very beginning, you have to think about there is something dropping which is not going to the inner cell compartment. Okay, so this is the second level of the compartment. Then the at what the rate it propagate here, it is kind of this is the amount where it goes. But often since they are interconnected, something comes back because your cell's diffusion process. In this way, you can have much more deeper level of modeling, but simple structure of compartment model is this. So idea is basically you have to find out this xt, how it changes over the different compartments in your body. So here, so basically you can have multi-level, basically deeper, upper, inside, all sorts of levels you can measure. So D dose at time 0, xt is a drug in the blood compartment at time t, then in the deeper issue at that time point t, and these are the rate of transfer from between the compartments. And there is always some removal is there. This is a very simplistic structure we are trying to build up. So how to represent this whole thing? Typically you can represent the whole system. This is, you can think about a system by these two differential equations. Okay, and you can solve it and you can then try to give that represent the whole system using this differential equation, but really it does not help to understand the whole process better, in a sense that you really like to have much more specific, like given this time, given this cell, what's the rate of change? Is there any parameter which I can control so that everything has to be a lot more better understandable? Or in other words, this may not have very interpretable things which it's just the system, it works like a black box type of thing. So you can solve this thing. If you solve this whole differential equation, then eventually you can boil down this thing something like this with 4 parameter model. Beta 1 exponential minus beta 2t plus beta 3 exponential minus beta 4t. And this type of things is very much interpretable. We can interpret
xt equal to this one.
xt equal to this one. Yes. Okay. So yes. So these are the, now you can think about this is a parametric function. So what you have done essentially, you extracted the parametric form from the differential equations, and as the way you have done it, so that each one have some interpretation, so that you can control. So if I know the value of these things, I can know exactly what the blood concentration level at each point. Okay. So all these constants, everything is absorbed in this parameter. In our regression setup, we can think about these are nothing but the regression parameter. All right. So the pharmacokineticists are often more interested in the values of the parameters than their actual profile itself, because that's what the parameters has its meaning. So this suggests that you have to solve a model like this, but by definition, this is clearly a nonlinear model because the coefficients are not linear. And another thing you might notice that you have only one covariate, but number of parameter could be more, like here 4 parameters. So here not exactly the dimension of the beta exactly equal to p. So number of covariate could be r, number of parameter could be p, p could be bigger than r, p could be less than r, it not necessarily it will match. Okay. The first thing is that how do you solve it? So it is different than in the morning what we have done in the logistic regression. That is nonlinear with the link function, but it was linear in the regression surface by taking the log, or in other words, in log scale that was linear. But this type of function, even if you take the log scale, it doesn't become the linear either. Okay, so that's what it creates more complication than in the morning one. So how do you solve it?
So can I do something like suppose I have a function theta, and I can expand this function about
Yes. So or before that we can, what we have done, the main idea was, since this is, we have the response here, and if we like to, we know that this is not the deterministic representation of the blood dynamics, it is an approximation, parametric approximation of the true cases, so there must be some error. So you can think about that you have this y, which is actually your blood concentration measurement you are taking, x is your times, that equals to this plus some error. Now if I assume some error like 0 mean, constant variance type, then what I can do, I can actually construct least square type of estimate, y minus this whole thing square, and then I take the derivative of all these things. That's the way it would go. Okay, but obviously the solution won't be that easy because this part is nonlinear, so that's why derivative would not go through. So we have to do number of approximation, and those approximation we can do using the Taylor expansion. And idea would be, we all know from the numerical standpoint or computational standpoint, if I have to optimize this function versus a linear function, it won't have like Newton-Raphson algorithms you have to apply iterative way, so there would be convergence issue, all sorts of issues would be there. And but if I show the least square solution, what if you remember, it is actually the equation is x transpose x inverse x transpose, so beta equal to x transpose x inverse, so x transpose x inverse beta, that equals to x transpose y, right? And then basically that one you solve, and if the x transpose x inverse exists, then you just put it in there. But whole idea would be, here y minus this part, if I can write in terms of that stage, not the inverse stage, x transpose x inverse x trans the beta, that equals to x transpose y, some x, then what I can do, I can actually use that routine, because after that your computer will go from there, because there your computer do the inversion, whatever it is. So then it will be, I should be able to use your existing software, which is highly tested, because if I write the new test software, then essentially no guarantee that it will work, right? So idea would be, as much as possible I'll feed in to your previously developed software, which is heavily tested already. And how much I have to go? Basically, as I said, that the structure is x transpose x beta, that equal to x transpose, that equal to y, that equal to y. That's the structure I'll show you, right? Then in the computer system, essentially you have to give some kind of x, some kind of y, then it will work in that equation. So let's, if I can work it out, it will see that it is possible. So of course you have to make some of the other assumptions, but I can talk to you. So if you had done some of this, yes, go ahead.
What you said about the non-parametric regression 2 days back, same thing here also we can do, because T belongs to some AB interval. So we can approximate by arbitrarily large linear model.
We can do, but we cannot do, because here the data set is very small. So yes, theoretically you can do, practically you cannot do, because number of observations is low. So basically another, so as I said, that to solve this thing you have to have some error term. So error term means statistically you have to put some stochastic distribution. If you put a constant variance, then it might look like this. Anybody can have any idea that why it really makes sense why it would look like that, because of the constant variance?
Constant variance of what? Error?
So error, because that's the simplistic thing we can think about, that you have the regression part is the nonlinear, then you have to put some error part. Noise, what we say. But noise has a constant variance, that's the usual assumptions we make. And usually it works well, right? But here also I put that thing. But if I do this way, then it's kind of regression diagnostics. It shows that it doesn't work. And I can say that right at the beginning, I shouldn't have started with constant variance. Why it is so? If you remember the experiment, that was all time series data. So it's a dependent data, right? So for a dependent data, error usually does not follow constant variance. You have to do something more. Cannot work. You have to go with like it, yes, or you have to put another level, like if the error equal to autoregressive process, some of the things you have to do. So in other words, we have to bring some heteroscedasticity. But if you bring the heteroscedasticity, so basically then what is the proposal goes to, that this is again still we are in the mean, this is the mean function, which is the function of the beta, and variance, that is heteroscedasticity, which means that it will depend which level of x we are talking about, because variance is changing at the different values of x. That's why, so truly I should have written xj, but j means essentially it is changing over this x. Clearly here beta equal to p by 1 matrix, but x could be r by 1 matrix, r is not necessarily equal to p. That's what you have to say. So this is the thing. Now you got it. But if I do this way, then you can see that here, right here, as many observations, that many parameter you are inducing. So total number of parameter goes more than the number of observations. So it really does not work. Theoretically, you can do that, but so what you have to think about, you have to do something which represent different variances. One of the easy idea is that since it depends on your kind of the feature vector, I can make it some function of the feature vector. But this is known as a result, if you assume some functional, non-functional form with x, that should be all right. So call this thing as, say, wj, where wj is a function of x. Then I don't need to estimate this whole thing. But still it is varying. Okay? So that's why basically the concept of the generalized least square thing comes into the picture. So basically I'll be skipping, so the first part, how the way we are solving, I'm skipping that part. So something like that. One proposal is that you can do sigma j square equal to sigma square w j, where wj is known, but still this means that you are having different variance for different point. Okay? But you have to assume w known, otherwise again it doesn't work. If I do that thing, then essentially I have to solve this part. So I will take the derivative with respect to beta and I solve it, right? So under the Gaussian likelihood, you can do all sorts of things, but let me go to the right place. So basically you will be doing the Taylor expansion. Okay, so you start doing this way, as you have said. First, that this is a nonlinear function, you make it some linearized way, and then what would, so the pivotal quantity was, this was the pivotal quantity. Why this comes? Because initially this was a square, then you are taking the derivative with respect to the beta, so that's why this is the first derivative with respect to these things. But what is this thing? We don't know yet. So what is the idea is that you expand this thing, then collect some of the terms here, then do some algebra right here. Okay? So because it is then not the square, it is just 2 terms. Here you can take 3 or 4 terms. All these things you can do. So you can do some approximated way. So this is the process goes. Whole process you can do pretty simplified. So what is the idea has to be, you are expanding with respect to some value. Again, here the mathematics might fail in practice, but mathematically everything is fine. So if your beta star in the neighborhood of the beta, or the beta is the neighborhood of the true value beta star, this guy could be very small, and in that way you can actually omit higher order terms. You just work with the first order terms. That's what we are deleting, essentially all the quadratic terms, etc. Now anybody can get the sense that why Newton-Raphsons oftentimes fail if the initial value is not close to the true value. If you understand the whole Taylor expansion, it will tell you that if the initial value is not close to the true value, it will fail. Okay? Then yes, yes. So you keep doing this part, and after you need to do a little bit more algebra, and then what you have to come through, you can collect all of the derivatives. All of the derivatives, note that here the transpose means this one has beta 1, beta 2, beta 3, all these parameters, and function of x1, x2, xn. Collect this thing as if your x beta. So it is not truly the xx, it is the collection of all first derivative of your mean function. Okay? And this one is the collection of just the mean function f of at x1, f of at xn, so that is it is n by 1. So everything is a function of the beta. And this w is a diagonal of w1, wn, which we have defined already. If I can do all this part, then again after doing all this approximation, you can actually write the iterative equation at the a plus 1th iteration. The 8th iteration, this inverse x w y minus something. Can you identify that it is exactly look like your least square solution? Least square solution is x transpose x inverse x transpose y. What it comes? The w comes this side. Another thing is the centering things comes, and this x are not that original x, rather than it is a function of the or the first derivative of your mean function, and as well as the mean function collection of all these things. So basically these are all function of beta, and that's why you need to do the iteration way, because this part everywhere we have the beta. So you get some starting value, get this one, whatever you get, plug in back, do these things, in this way it would go. But what is the idea? So once you have this part is common with your software, what you have developed already for least square thing. So from here, what you need to do, as you need to put that x, this is the new x, as your input matrix into your software, and then actually here you can manipulate a little bit further. With a good choice of w, you can make it extra so that it would look like extra time, extra inverse, all these things. But main idea is that since I am losing some control because of this Newton-Raphson type of algorithms, at least computationally you will get, the software will be much more stable if I can use the least square type of computational tool. Because I have to do repeatedly, I have to calculate all this part. So that's what you cannot just, I have noticed that sometimes computer scientists started doing, okay, I have a function, I just throw in the function in an optimization routine and let it solve. And you will see that it does not really give you the good solution. Otherwise, we would have done maximization of the whole likelihood, not the log likelihood, because there is a number of reasons why we do log likelihood instead of likelihood. It is just not that one-to-one function. Beyond that, same way, you should not throw in whatever the nonlinear function into your machine and machine will solve it. It's not true. So you solve it and you get the solution. Yeah, convergence, all these things could be very much issue, but eventually you can estimate all these parameters, sigma square is exactly the same way, all sorts of thing. And you can prove this again, consistency of the variance component, consistency of the beta, all sorts of things you can do. Okay? So that's the idea of the nonlinear regression. So if I collect all this, whatever you have seen, so basically the nonlinear regression I can write down nothing but like this simple structure. Here is the q dimension, gamma is the kind of the regression coefficient, but that's a p dimensional. It does not need to match, and you need to have some assumptions is there. And very simplistic way, we can, so these are some more examples, probably that exponential nonlinear through this gamma 1, gamma 2. This is also nonlinear. Note that even if you take the log, it doesn't become the linear. So these are typical example of nonlinear regressions. But this type of function has lots of applicability. That's what I just showed. But most important thing, that number of predictors is not same as the number of coefficient, which was the case in a linear model. Okay. So typical way, you just solve this thing with respect to gamma, or you bring here some W matrix, but W matrix doesn't have any parameter. That's what, just as a structure way. So what I'm trying to say, that whole picture, what you see, it looks like simple here. And what does it look like? Look like just essentially least square type of things, right? So, and I showed you already how to do the solution. Yes.
So does the initial choice of beta
would have big impact
if the loss function we are minimizing is convex in beta?
Loss function we are minimizing.
Most of the cases it is convex in beta.
Because I mean here the loss function is square error loss function, right? So if this function is convex in gamma in this case, so would it really matter? I mean, whatever initial value I choose, if
it would, you can try, just forget about so complicated, just logistic regression, try with logistic regression.
Logistic is not, I think the
no, it is, you can have the same way. Here essentially what you will do, logit inverse, you will put x transpose beta.
Yes, but that is not convex in beta, I guess. So my question is, if the loss function is convex in...
No, here also you cannot give this, that guarantee you cannot give here, because this function,
we do not know the nature.
you don't know this thing. So it has to be well behaved function. Only thing then you can say that it is you can assume that it is second derivative is well behave, third derivative well behave, then it might, but in reality it doesn't work. So I got your point that you'd like to prove that this is a convex function, but then you are assuming f has to have a good behavior or the good functional behavior. But no way you can give the guarantee because it has to come from the data. So it may not happen. So in other words,
Monobody's point was that possibly if it is convex, then it doesn't matter from where we will start the computation.
So it will anyway converge to the global minimum because the convex function has a global minimum. So
Strictly convex.
Strictly convex function. Yes.
Then what's your
No, even if it is not strictly convex.
In that case, it may not have global minimum. In that case, it may have this one.
so
It may have this one.
anyway, so many. Let me give you what's the other example would be. Suppose the true curve look like a normal, right? So to approximate the normal curve, you need two parameters. But at the beginning, you just do not know. You kept this third parameter because you are doing non-parametric thing. And if the really true curve is the normal, you will see that your computation instability because there is no need of the third parameter because curvature only described by the two parameters. So third parameter is invalid. So in that way, you really do not know which one is doing exactly how much and how much information is there. So if there is not enough data corresponding to this particular parameter, first thing that will create the problem, no matter whatever you start. And in general way, any kind of nonlinear optimization, it creates the problem it's a generic problem of Newton-Raphson type of algorithms. We can say that, yeah, if it is convex, because we proved this thing in even first year BSc that you proved that if it is a convex, then their convergence is guaranteed, all sorts of things. But reality, it doesn't work. It all depends on the really how smooth it is, how the most smooth the second derivative it is, all sorts of things are there. So that usually I try to tell my students that first before you go further, you look at the gradient vector. How does it look like the gradient vector? That first derivative of your f, that will give you some idea of what you are trying to do. Okay, good, very good. So anyway, here another idea was that really in practice it will have the problem, but in nice thing that what I am trying to do, we can structure everything kind of a generalized least square type of estimate and show that you can actually use the existing type of software. So in terms of the programming, in that would be much better, although you need to do lots of derivative etc. to come this thing. So that's the case. I will skip this part additive, all this backfitting now. So coming to the lot more really what is nonlinear or the machine. That's what we, for this big data or everything, we are going to solve this machine now. So what is neural network models? It existed actually for a while, but now it came back with this big data things, all these things, it came back again. In fact, I published one paper in JASA one time, and then I thought that it's not a good thing. I left it, leave the things. Then it's coming back, and I think that my students can do a good thesis out of this thing. So, but it's a different way it came back. It's not exactly the same way. So typically, you model the response as a nonlinear function of various combination of predictors. Before that, how about I ask you this question? So suppose my data set X is a matrix. The predictor, the feature vector is a matrix. And this morning we talked about the logistic regression. It's the very good classifier, right? So if the data is a matrix, how do I do this logistic regression? If the data is a vector, that's we have done already. You could put the regression way, right? But if it's a matrix, how do you do that? Everybody is getting my point, right? What I am saying. So the feature is observed, it coming as just a vector, as a matrix, not really a single value. So how do I fit that logistic classifier?
So instead of taking inner products of the parameter, and in logistic regression we take e to the exponent of.
So you have actually G inverse or say logit inverse. This is I have. Okay. So what do you like to do?
Can we work with quadratic form?
Why? So you will take this plus all this p, take it, and then you will take x1 square, beta p plus 1, all these things. So already how many parameters you have? If it is say r by r, then here you are putting r by r parameter already, because this is one of the observation. This is one of the observations. So this is you are putting r by just this one has r by r parameters, right? And then if you take the square, probably why you are taking saying that you will take the square, because since it's the whole matrix, this and this might have some interaction, this might have nonlinear things, so you might say the square. So if you in other words, what I'm trying to say, you are going to collect all second order term. But how many second order term would be? Totally you have r times r. So r times r choose 2. Think about r equal to just 6. So second level it will come 36 choose 2 parameters. So mathematically I can think about do this part, that part. Again still this would be the approximation, because this really does not represent the whole matrix, right? Even if you do this way, suppose if I can do this way, it does not represent the matrix, right? It's just an approximation trying to do. But you can do you can try, but idea is that really it is not the right way to do. So on the other hand, so if the main idea is that they are not completely separated, they are kind of interrelated, so what should be the way I can use this whole matrix information? So look at this neural net very carefully. That's the way actually I came into the business of the neural net. You can use for other purposes as well, but it probably would make sense for the matrix of data. If your feature is the matrix, then probably neural net could be. No way I'm saying that this is the way, this is best way, but this could be. So because that's what our discussion. So that's what let's define. So what it is nothing but, in my opinion, it is just a combination of nonlinear functions, bunch of nonlinear functions. It contains lot more parameter than the corresponding. If I could do the linear model, still it will have p, which is times r by r parameters. But if I construct a linear neural net model, it will have a lot more parameters. If I would have done this way, I know what is the interpretation of the parameter. If I do neural net way, there is no interpretation. So only it's a mathematical approximation. For that purpose, we are doing this thing. So immediately what it should be over parameterized. It has no interpretation. It is very, very difficult to optimization than doing this thing. Okay? So then why you are doing so? Generally good for prediction only. And also it requires a very large number of data set. Then you can do that. Okay? So it has lot more, I think, the dirty side rather than the good side. And that's why the statisticians did not pay much of attention until very recently. But for the machine learners who like to make garbage in, garbage out, because they always think that this is a machine, that's what it's fine. Okay? But it's the time probably we have to look back. Whoever will be working in a big data, that's the case should be. So here it is now, time for me to show you how it is related to the linear model. Think about the linear model. You have a response. If you have a p features, then beta 0 x0 plus beta 1 x1 plus beta 2 x2 beta p x1, right? This is your kind of the feature. This is the response. you are just linearly related all of them in additive fashion. What is a neural network? A simple network is there is one hidden layer. This hidden layer doesn't have at this point any physical meaning. But what is this thing? Then when you have this feature is not directly connected to the response. So this one is maybe your brain. So it is not really connected directly, but this one is connected to, this one is connected to this, all of the feature connected to this, then all of the feature connected to this, then all of the feature connected to this. So you can think about that this guy is linearly related with all of them, this guy again linearly related all of them. Then in the second layer, so after it's the first layer, then all of them are again connecting the Y. Since this one is connected all of them, since this one is connected all of them, then when I'm making the connection between these two, automatically the interactions come in. But how the interaction come in, I'm not trying to explain at all. That part already we accepted the fact that no way we try to understand how the way it is propagating, but something is going on if I do this way, right? So that's what the concept is, that if these features are somehow interrelated, probably instead of this type of network or this type of connection might work better. That's the idea behind this thing. So now if I try to model this whole thing, how the way it will go? Couple of remarks. The explosion of the data and low computing cost accelerate computer-aided techniques. That's fine. Neural net can model complex system by using nonlinear functions of various linear combination of the predictor. This machine has large number of parameters, thus requires large number of data set. It is very, very important, otherwise it cannot work. And so coming back to this thing, this is my response. Note that this was the notation. This you can think about again. If I go back, basically you can think about this is my response with respect to this thing. This guy is, one guy is here, so it will be linearly related here. Then another y is here, it is linearly related here. Another y is here, it is linearly related here. And then these guys would be exactly additive way, it would be related to this thing. So that's the things I'm going to write in with the notations. So you can think about this was the score from the hidden node number 0. This is the score, hidden node number 1, score at the hidden node number m minus 1, because you have m minus 1 node. But these guys are actually directly connected, or this guy calculated directly from the feature. So this one has some of the alpha vector, so this guy is some of the alpha vector or all the feature. So this is directly connected with the feature, and y is connected through this node. And what is g? At the beginning, instead of writing in a identity function, some function think about, okay? It could be nonlinear function, but some known function. But it's kind of a generalized linear model, like logistic regression, this could be logit inverse, right? Y equal to logit inverse, that type of thing. It's a linear function. Then since h, these are all function of the predictor variables, or this is the score, I break it up, this piece equal to this thing. So I write all these things in this way. So what do I have? As many node I have, that many beta, and each node has as many feature, that many vectors. So this you have m minus 1 vector of alpha. Each alpha of length is p minus 1 or p, whatever the number of feature vector. So in general way, I can write it down as a function of the feature vector x, alpha 1, alpha 2, alpha m minus 1. These are all vector. Beta is all vector like this. So now look back again, the nonlinear function I showed you, it is nothing but y equals to some nonlinear function plus error. Make sense? Typically, these functions gy, g1, g2m, gm minus 1, these are called the activation function. Okay? So common choice, what the activation function you take, common function is the logistic choice. So why it is logistic? So everybody is clear, right? So this is nothing but a nonlinear model, whatever we studied. So the neural net was first used to model the human brain. That was the reason, but it didn't really go through. The model represented neurons, and the links between neurons represented these synapses. And idea is that one of these, so there is a threshold. So basically when the signal comes, if the signal is bigger than some threshold, then it fires, otherwise it doesn't fire. So that's why this activation functions comes in. So at the beginning, that's why activation function was a step function. So if there is below threshold signal, it's flat. Once the signal is up, it is up. So that was the beginning. But later on, it changed by logistic activation function, because again, logistic has number of good properties, etc., etc. It can create a little bit of smooth function, and you can use some radial basis function, all sorts of things. You can do these things. Okay, so that's not the main purpose. This is just anybody can do difference. But whole idea is that you use some kind of activation function, which would like you have seen that logistic function also works. That in boundary region it's kind of inactive, at the real region it kind of active. That's another reason why you can use the logistic. So some logical way you can put this part. But next I'm going to show it that it is nothing but nonlinear. So I showed you it's a nonlinear model. Now I'm going to show it. It's not nonlinear model. Actually, it's a linear model. So take the special case. If all these things are kind of identity function, it's a special, because that's also the neural net. Then this guys becomes like this. Then each of this piece you break it up into this linear score function, sum over xi transpose beta. Then you do these manipulations, collect all of this beta. So this is kind of your intercept term. Then this is kind of coefficient of the first feature. This is coefficient of the pth feature. The coefficient looks very complicated, but doesn't matter. These are all constant. So give a name, say derive the beta 0 star. This is beta 1 star, which is a number of parameters are there. This is beta p star. Eventually I can write that expected value of my response that equal to beta 0 plus beta 1 x1 plus, and these things does not change. These things are your feature as the way it came. P minus 1 exactly in a linear model, as many feature, that many parameters you need. In that way, that many parameters, at least in representation. But inside story, each of them has tons of parameter inside. But I can write down in this way. Then if I can write down this way, then I can get this beta 0, at least by structure, this beta 0 star, beta 1 star, beta p minus star, just by doing the least square estimate. Whether it will work or not, that's now we have to dig in. But essentially, I can write it down, and what it helps me to develop the theory behind this part.
So, could you please go back to the slides?
This one?
No. Yes, this one. So, here we can take xi to be vector as well.
At this point, I am not saying xi is a vector.
Not in the first model, the second model.
Yeah, it is not. This is just like your one covariate, second covariate, third covariate, p covariate. So
Can we consider xi is
vector?
yes?
Yes, we can.
So this solves the problem regarding the problem you are discussing. Right?
No, this solve this thing, anything here, x1, x2, xp, p, this one, 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 all of them, as the way you wanted to do. This is the first part. So I'm not taking it as a vector way, because that may not make sense, because even if it's matrix, this column by column may not make sense. Idea is that we don't know any relation between all of them. So that's what these are kind of independently you are putting. But they become dependent when it is propagated through this guy. through this channel, if it doesn't propagate it through this channel, then they are essentially hitting independently. But once it's passing through this channel, then they are not going here indirectly, because this one has all of them, this one has all of them, this one has all of them. So they have to interact. How the way they interact? God knows. Okay? So it's in that way, it is a very beautiful idea behind, if you can try to, if you understand everything what I'm trying, in my opinion, it was very beautiful idea, but at the same times, it's kind of showing your hand to chiropractors that, okay, you will be somebody like that without any reason. So it might look like that, it might work, but we don't know. Okay? So, yes.
Will we introduce another, let's say, we introduce another level in this network. So the number of parameters will be
increasing exponentially. So that's what, yeah, you
how
can.
do we handle such cases?
That's the problem, that unless big, so not only that, there are a number of issues, like even how many will be here, we don't know. So generally, people in practice, you start with some number, and hardly, if you have to use too many layers, probably you may not believe that one that much. But we can use the second layer, third layer, and then develop some of the deep learning type of techniques that is doable. But again, I have no way of saying, unnecessary, you may make your, break your computer. That's what I can say only. Whether it will improve or not, I cannot say. But I can definitely say that you can break your computer at certain point of time. Truly, because I don't have much of explanation. Only I tried to look at whole thing, how it is related to the linear model and structure, then because I wanted to do the theory here. Okay? So, but it is interesting to see that how, what we started, what I said, that very simple linear model, that how powerful it is. The big machines you can put this thing. Now go back, same way, last page, essentially how to do the estimation. Since it has tons of parameters, really you cannot estimate, even for large number of things. So this is your kind of the least square equation, and then you put a penalty function on all these things. But the penalty function would look like here. It's not L1, not L2. It's, I don't know. But this is the kind of the stage the computer scientists are solving this way. Then how to select the lambda. They also say that cross validation. But think about even running the whole neural net in one time is too difficult. Then if you do the cross validation, it would be even a lot more cumbersome. Okay, but that's the kind of this stage, that this tuning parameter is there. How the way will choose this p lambda, all this. So machine learners, they know probably everything. I don't know that much, because I only try to understand what's going on. But if you tell me whether it will work or why it doesn't work, I would say that probably I cannot say. Okay, because still it's a mystery. If it works, why it works. If it doesn't work, why it doesn't work. But I can see some connection, that if these features are very interrelated, this is one way I can capture the interrelationship. But how the way it is being captured has no clue, because we are not using you can see that this type of things we could have done on LDA using some multivariate normal. Those type of things we could do, right? But that's how not we are doing anything. All right. So as per our expectation, that this was another example at the day 1 I started with. You have handwritten digit, and automatic, you take this image, and then you have to basically identify whether it is 1, 0, 2, 3 or 4. Then you can sort your all these envelopes, like millions of envelopes, pretty quickly, and you can save a lot of money. So how the way I'll do this thing? Now you have learned lots of classifier, how the way we'll do this one. You can do, that's fine, but how would you do if in nearest neighborhood? So some way, let's make it short. So this is basically very well tested data set. You can Google it, MNIST database, handwritten digits, which is a training set, 60,000 examples. The first thing what I said, that those type of machine can work only you have really large number of, but flip side is if you have really large sample, then your machine takes 2 days to run. Okay. So for example, this one you can run in your laptop. I'm 100% sure it won't work. So 60,000 examples, that means 60,000 cases you have, and in the test set you have 10,000 examples. I think the original data set has even more, but this one my student could do so far. Okay. Because my students are not from computer, although some of them has computer science background. Like right now the guy who is doing, he's an electrical engineer. So there are 10 digits from 0 to 9. Note that, as I said, typically when you take the image, then image is essentially portrayed in a matrix notation, matrix form, and typically it is say 28 by 28. So the data comes for a single digit as a 28 by 28 matrix. So here is kind of 28. It could be different, but just for our purpose, let's see 28. So whole thing, if you go to the data site, it is there. For anything, the data is there, it's stored, but in a numerical way also it is available at this point. Okay. So since you also wanted to have more layer, what we tested, simple, but we put 2 hidden layer. Why did we do that? Because we thought that here you have the 9 component. So y vector is a 9 component vector. Typically, if you do the multivariate regression even, you should apply that PLS, but if you do the PLS, then you are reducing the dimension. Here we cannot reduce the dimension because 10 dimension I have to work it on. All these 10 digits are important. And number of nodes, we choose just 128. Don't ask me why 128 at this point, okay? But we chose, because he just did it. Probably his computer works 128, so he did 120. 128 is huge. Then what would happen? How many feature actually have? Or how many dots you have in this X matrix? 28 by 28, 784. So that means 784 coefficient immediately there for each of the one neuron. So that means at the first level, you get number of coefficient equal to 784 times 128. You can calculate how much it would be. And then we'll have the second layer. Then there are another 128 of them. I'll show you a little bit more. The number of input layers would be 784 and the number of output would be 10, because output is a 10 dimensional. That's what we have understood. The input data training set, we can say denote it that Xij, J for this individual, like 60,000 individual images I have. And I is 784, it is basically 1, 2, 3, any order you can write. And of course the output data is, you can write as Yk, again J for the 60,000, K goes from 1 to 10. So the structure of this layer would be, you have 784, that the pixel, and then the first hidden layer, as I said, 128, but each of them connected to this one, each of them connected to this one. Then once you make the score, then you need 128 coefficient to connect one, another 128 coefficient to connect sex one, another 128 is here. Once you have here, then since it is 128, all 128 would be connected to this, another 128 would be connected to this, another 128 connected to this. Okay, so you can imagine how much parameters already you injected. I wish that I could solve it just simple linear model. So a little bit more notation. This is your basically input vector. I wrote basically in the matrix, in the whole matrix in a vector notation, because essentially the original data is the matrix, but you can read it in a vector. So this is the weight matrix for this first level. It would be 784 for this 784 features and 128 hidden things. So that's what 128. And this is at the second level, 128 by 128. That goes in the second level. Then in the output, you have 10 outputs. The first row for the first output, second output, 10th output, but 128. And then this is from the, you are getting to the output vector here. Then you are calculating the score at the level 1. At the level 1 score is, this is the weight matrix time this is the feature vector. Weight matrix, feature vector, 128 score you are calculating. So all this matrix calculation would go on. Then from there, using some activation function, you calculate the scores, right? Because we use some activators function. Once you have this thing, go to the second level. Now this becomes your input vector. So note that we are exactly trying to follow the linear structure piece by piece. And then this has become the weight matrix for the second one. You calculate again score for the layer 2. Once you have the score layer 2, then it will connect to the output, right? So first you create this activation function for each of from 128 from the second layer. And once you have this thing, you calculate these are this score coming from the second layer hidden, second hidden layer, or the nodes at the second layer. Then these are the weight matrix. This is the score or the final y bar you are calculating. Then you put another, basically the activation function, transform it to the what should be the original one. So this is your output vectors from this score. You are calculating this whole this part, and you are replicating, do some algorithm. So I don't know this algorithm yet, but backpropagation algorithms he did. If I did it, at least for this example, for the training accuracy, it is about 85%. And testing accuracy is also about 85%. So in that sense, it is not bad. It is pretty good. Because this type of job, if you can do 85% correct, this is not bad. This is not that sensitive, so 85% is okay. When 85% is not okay, like if you use the iPhone 10 and recognition is not right, then 85% correction is not okay. People will not buy the phone, right? It has to happen at least 95%. Although now claim is about 99%, but I don't believe. I have to check with my own phone, but so far so good. It is not bad. Usually it works well, yes.
How fast is this algorithm? Because
I don't know. I don't know. You have to ask my student.
Because if the activation function is of logistic kind, then for each of those components I have to run an iterative algorithm. So
Yes.
The way I see, I mean, the time will blow up.
It can blow up. It can blow up. So that's what I don't give this problem to any of my stat students. I told you that his background is electrical engineer. So he knows definitely a lot more computation than me. But that's what his work. He has to develop, and then I'll support him the theory. But then we will be ready to go check with face data, face recognition data, all sorts of things. But this is the existing data set we have to try for. And another thing for you guys, particularly those who are learning, you can see why not I can do a logistic regression, how much accuracy I lose. Because if I go for commercial purposes, developing this machine is lot more expensive than developing a machine with the logistic regression, right? So how much accuracy I lose? It's a trade-off, right? Because in a real situation, in mathematics class or this class, okay, we will be talking 85% to 87%. Oh, mine is better. But in reality, I don't care if to do 87% if I have to spend another $1 billion. Come on, you take your machine back. I'm fine with whatever I have. So practically, I like, particularly the data science group, they should try with some simpler thing given their context. Because these things, doesn't matter whatever the algorithm you use, again, no algorithm could be foolproof. And no algorithm can be as fast by a single day you can get the whole output done. Because with this so much data, 10,000, so truly what your CEOs are asking that in our company there are tons of data. If you are working, you use the data, right? So 60,000, say for example, if for the company like Amazon, is no big deal. They have 60 million records probably every month or so. So why not you are going to use 60 million of the records? But your machine really does not capable of handling 60 million. But then what's the data science perspective come in? Do I really need to look at 60 million records? You might have the 60 million records. I only look at when there is a different handwriting is coming up. Because if it is the same handwriting repeatedly, I might just need few of them. I don't need all of them. So truly, if I use all these 60 million, because Amazon has 60 million records, I have to use it. That's a dumb way of doing this part. Then that means you are not doing the data science at all. Make sense? Okay. Sounds good, right? You are too late. We are done pretty much. Not pretty much, actually we are done. So let me see if my internet works or not here. Any comment? How do you like so far? It looks good, looks interesting, but you have to think in that way, so it should be okay. But as I said, that doesn't mean that everything is ready. But nevertheless, it is time to look at. Anyway, I don't have this part. So I think by saying this thing, so it is also time for your coffee or tea. But probably, I think I like to basically thank you guys for listening me. This is the, I think you can stop because you don't need to record, right? Or you can record, that's okay. So I'll say just a few sentences. So I just checked via that what Professor Dhar put in kind of the agenda, like 10 of the things, complexity, understanding the complexity of the data, then some of the methods. I'm pretty happy that we basically touch base fairly good number of things. What I feel that probably we could have done some more computational aspect, little bit more, but within these 4 days it is not possible, and then I need a lot more equipment as well. So probably that could be a separate one where we can emphasize more on the just applied side. But it is essentially important for you to learn some of these modern things, even if you see that some of the old thing I am using, but there is a modern version of all this part. It's kind of putting the old wine in a new bottle. You have to do it because that's the way it's the wine culture. Same way it is the culture you have to. It's not just you are pouring this thing. There is a reason why you do that part. Okay, I told you at the very first day. Did I say that like data analytics with wine is a very hot topic, because wine, to the quality of the wine, the cost of the wine depend in so many factors, and it's a so billion-dollar business. If you can predict what would be the next market, like right now everybody is saying that China is the next market, but really what should be the consumption over China? and which kind of wine. There are so many thousands of different types of wine. It is not just our tea. So that's why it is a lot more challenging. But wine culture is very different. You have to change the barrel time to time. If you do this time oak, next time probably you will be using different types of barrel. If you keep in temperature, say 30 degree for 2 years, probably you will keep it 35 degree another 2 years. So all sorts of things are there. And then you make a good wine. So to make a good machine, we may have to use some of the old stuff, some of this new stuff, what we have been talking about, and then all these things would. So I hope that you guys at least or learned something. And as I said, it was my pleasure to be here. This is the probably first time in 20 years I spent 5 days just fully academic campus. In India. You are right. I have spent more time academic campus in many of the other countries, longer than even 1 week. But in India, this is fortunate or unfortunate. I would say the unfortunate. I should not be very proud of that. But that's the way my life is. But hopefully, I was hoping that you guys have a lot more people. Eventually, we can have some team build up where we can interact each other and try to solve some problem. Like many of the problem I introduced you that with the data set, do something. Like for the IPL data, you do something. You do some creative way because you guys are all smart. Why not? And I'm trying to give you this way that it is nobody's single body's work like statistician, mathematician, computer scientist, not like that. You do something and go and get the validation, like throw with the audience what they think. Even if it is a trivial solution, does it make sense or not? But if we don't try anything, and if we keep saying that, oh, this is an obvious problem, neither work. If you don't try, that doesn't work. If you just say that it is trivial, do it. And see whether really people throw it because of the triviality or because it doesn't work. Most likely that people might throw it like the common people, it may not work. So that was one of the things, but hopefully we'll be in touch. All right, thank you.
Thank you.